So, hi everyone, this is my video to display to you the proof of to the adiabatic chain equation, and this we learn in Thermodynamics 1. And we know we have this shown to us that it is for a monoatomic gas, that it is it's a relationship between the volume of the gas and the temperature. So we know this, that we can write it like this. Vt to power 2 over 5 is equal to a constant for a monoatomic gas. But how do we actually get to this? I've always wondered how we do. But I want to share to you a very simple proof and just include some basic calculus, some basic integration, and some the first law of thermodynamics, of course. And then we have, so to begin, we can start off by looking at the first law of thermodynamics and what an adiabatic change really is. So I'll use blue for the first law. And we know the first law of thermodynamics. So I can write here first law of thermodynamics is the conservation of energy, which in the thermodynamic system is written in this form, where Q is the heat supplied into the system. The delta U is the change in internal energy of the system, and the work done is work done by the system. And we're talking about ideal gases here, so work done by the ideal gas. So it basically tells us that the heat supplied into the system either goes into increasing or changing the internal energy of the system, or results in the gas doing work on the surroundings. So we can start from this, and we know that an adiabatic change, I'll use here, adiabatic change is such that the heat is equal to 0. An adiabatic change, so the heat transfer, is such that Q is equal to 0. And we know this because it happens so rapidly that no heat transfer can take place. So we can start off by just rearranging this, and then this can be our first step. So we get, therefore, 0 is equal to delta U plus work, and therefore delta U is equal to minus work. And this we can all see. This is trivial. But in fact, proving the relation between the volume and temperature is very simple too. And this can be done by some additional knowledge, which we also learn in Thermodynamics 1 itself, being delta U is equal to NCV delta T, where the CV is our specific heat, molar specific heat capacity at constant volume. And we know the work done is, of course, the integral PdV, where this is, as we can see, this is the area under the graph of a PV diagram. So if we think about this, we get NCV. So in fact, we can reduce this expression and make it a bit easier as well. What we can do is we can call it d work and du. So du is equal to minus d work. So we're looking at small changes, and then this integral goes away. We can just talk about the minus PdV. So we get implied, therefore, NCV dt is equal to minus P dV. And this is the expression that we have now. And actually here, we're almost there. All we need to do is we can just say, use our ideal gas equation. So I'll write here in blue as PV is equal to nRT. Therefore, we know the pressure is equal to nRT over volume. I'm just substituting in pressure because we're trying to find the expression in terms of volume and temperature. we know that there's also the expression in pressure and temperature, but that can be derived from the other one. So nRT over V. And we can just use that here. So we get right here, and therefore NCV, dt is equal to minus nRT over V dV. Therefore, the NN cancels over, and we get CV dt is equal to minus R T over V dV. And now let's just rearrange the variables. We know R and C are constants, and we have a dt on one side and dV on the other side, so we can just do CV over R times dt over t is equal to minus 1 over V dV. And now we can just integrate this expression. So when we integrate this, we get CV, because it's a constant, it comes out of the integral dt over t is equal to the minus the integral 1 over V dV. And we're almost there. All we have to do now is we can just say we know, so we know this. This is just as integral of 1 over x dx is equal to ln of x, indefinite integral, plus c, of course, but here we won't look at that constant. We can use we'll actually use the constant, but this will just provide, there's a simplification we can do later, so we can just do cv over r ln of t is equal to minus ln of v plus c. That's what we get. And we already see we have an expression in t and v, so we can just rearrange. But before we do that, we can use this, another thermodynamic knowledge we know for monatomic gas. So as for atomic gas, we know that our molar specific heat at constant volume is 2 over 3 R. And we know this. So what we can do is we can just substitute that already in, just to reduce remove the R. So we can say here we get 2 over 3 R over R ln T equal to minus ln V plus C. And if we remove the R, we get 2 ln T over 3 is equal to minus ln V plus C. And here we can just use some basic exponent laws. We know because it's multiplying the logarithm, we can just take that to the power. 2 over 3 is equal to minus ln V plus C. And I just realized I wrote something. I just wrote something wrong here. This is over 3, of course. Sorry for that. We can correct it. And this, we're almost there. All we can see here is, go here. Now we can just say, therefore the ln of t to 3 plus ln v is equal to c. And again, by just basic exponent laws, we just have, or in fact logarithm laws, vt to 2 over 3 is equal to some c. Therefore, v times t to 2 over 3 is equal to e to power c. And of course, e and c are both constants, c being the constant of the indefinite integral, and e is of course Euler's number constant, so implies we have proven that vt to power 2 or 3 is equal to some constant. And that is the expression, the relationship between volume and temperature for adiabatic change in ideal gas in a thermodynamic system. So I hope you enjoyed this video. And if you like the video, please don't forget to like, share, and subscribe. And I hope to see you next time. Till then.